When you look up at the sun, it seems eternal, a blazing sphere of fire that has illuminated the sky since the dawn of life. Every sunrise and sunset reminds us of its constant presence, unchanging through time. But if the sun has been burning for more than 4.5 billion years, why hasn't it run out of fuel? What exactly is it burning? And how can something so massive stay aflame for billions of years without ever dimming? To understand that, we have to start with a correction. The sun is not on fire the way a candle or wood burns on Earth. What we call burning on Earth is a chemical reaction called combustion. It happens when fuel, like wood or gas, reacts with oxygen, releasing energy as heat and light. But the sun doesn't have oxygen in that sense, and it doesn't burn carbon or wood. The sun's energy comes from something far more powerful: nuclear fusion, the process that powers the stars. Deep inside the sun's core, conditions are extreme beyond imagination. The temperature there reaches about 15 million degrees Celsius, and the pressure is hundreds of billions of times stronger than what we feel on Earth. Under such immense conditions, atoms don't behave like normal matter. Their electrons are stripped away, and what's left are bare nuclei, mostly hydrogen nuclei, or protons. When these protons collide with enough force, they can merge together to form a new element, helium. And that's where the magic happens. When two hydrogen nuclei fuse to form helium, a tiny bit of their mass is converted directly into energy according to Einstein's famous equation, E equals mc squared. That simple equation, energy equals mass times the speed of light squared, explains the sun's endless fire. Even a small amount of mass can produce a tremendous amount of energy, because the speed of light squared is an enormous number. This is why the sun can shine so brightly for so long, even though it loses about 4 million tons of mass every second, converted entirely into light and heat. But even at that incredible rate, the sun's supply of hydrogen is vast. About 74% of the sun's mass is hydrogen, and about 24% is helium, with trace amounts of other elements like oxygen, carbon, and iron. The sun is so huge, it contains 99.86% of all the mass in our solar system, that it has enough fuel to keep fusing hydrogen into helium for roughly 10 billion years in total. Since it's already about 4.6 billion years old, that means it's only halfway through its life as a stable main sequence star. Now, let's imagine what's really happening inside that glowing ball in the sky. Deep within the core, countless hydrogen nuclei smash together every second, forming helium and releasing enormous amounts of energy. This energy travels outward through a region called the radiative zone, where photons, particles of light, bounce around, scattering off other particles in a chaotic dance. It can take these photons tens of thousands of years just to travel from the core to the surface, losing energy along the way. Once the energy reaches the convection zone, things move differently. Hot plasma rises toward the surface, cools down, and then sinks back into the depths, creating convection currents, like boiling water in a pot. Finally, when this energy reaches the outer layer called the photosphere, it escapes into space as sunlight, the light that reaches Earth in just over 8 minutes after leaving the sun. That sunlight carries not only heat, but also the very energy that sustains life on our planet. Every tree that grows, every breeze that blows, and every drop of rain is powered in some way by the energy born in the heart of the sun billions of years ago. But let's go back to the main question. If the sun is constantly fusing hydrogen into helium, won't it eventually run out? The answer is yes, but not anytime soon. The sun still has about 5 billion years left in its current stable phase. Over time, as the hydrogen in its core depletes, the core will contract under gravity and the temperature will rise even higher. That will trigger a new phase, where the sun begins to fuse helium into heavier elements like carbon and oxygen. When that happens, the sun will swell into a red giant, expanding so large that it could engulf the inner planets, possibly even Earth. The outer layers will drift away into space, forming a beautiful cloud of gas and dust called a planetary nebula, while the remaining core will shrink into a dense, hot remnant known as a white dwarf. It will no longer produce energy, but it will glow faintly for billions of years more as it slowly cools. That is the sun's eventual fate, not an explosion, but a gradual fading into silence. So when people ask, what is the sun burning? The answer isn't wood or coal or fire as we know it. It's burning hydrogen through nuclear fusion, the process that turns matter into pure energy. And the reason it doesn't run out quickly is because the fusion process is incredibly efficient. Only a tiny fraction of hydrogen in the core is converted to energy at any given time, and the rest remains locked away, waiting its turn over billions of years. What's even more fascinating is that the same process that powers the sun also exists in every other star in the universe. From the smallest red dwarfs to the most massive blue giants, every star is essentially a nuclear reactor held together by gravity. The balance between the inward pull of gravity and the outward push of radiation pressure from fusion is what keeps a star stable. If the balance breaks, say when the fuel runs out, that's when stars collapse, explode, or transform into something entirely new. For the sun, that balance is perfect. For now, gravity tries to squeeze it inward, while the heat and radiation from fusion push outward with equal force. This delicate equilibrium, called hydrostatic balance, has kept the sun steady for billions of years. Without it, the sun would either collapse under its own weight or blow apart from uncontrolled pressure. Interestingly, before scientists understood nuclear fusion, people once thought the sun burned like a giant fireball of coal. In the 1800s, physicists calculated that if the sun was made entirely of coal, it could burn for only about 5,000 years. Clearly not enough to explain Earth's ancient geology or life's long history. It wasn't until the early 20th century, when Einstein and others uncovered the relationship between mass and energy, that scientists finally realized the sun's true engine lay in the atomic realm. Even now, the study of the sun continues to reveal surprises. For example, its outer atmosphere, called the corona, is mysteriously millions of degrees hotter than its surface, a puzzle scientists are still trying to solve. Massive solar flares and coronal mass ejections can blast charged particles into space, sometimes disrupting satellites and power grids on Earth. Yet, despite all this activity, the sun's output remains remarkably stable, a steady source of life-giving light. Every beam of sunlight that touches your skin is ancient. The energy it carries began as fusion in the sun's core perhaps 100,000 years ago, took millennia to reach the surface, and only minutes to cross the void of space to Earth. In that sense, when you feel the sun's warmth, you're touching a fragment of cosmic history, a pulse of energy born long before humanity even existed. So, the next time you see the sun setting on the horizon, remember, it's not simply burning, it's performing one of nature's most extraordinary acts, turning matter into light, time into heat, and gravity into balance. Its fuel may not last forever, but in cosmic terms, the sun is still young. It will continue to shine for billions of years more, a faithful star illuminating the story of life. Don't forget to like, share, and subscribe to WiseUse, where we bring the wonders of space to life, clearly, beautifully, and scientifically.